one. Now these are pretty simple geometrical objects. Let's try to focus on something else. We want to compute some more complicated cases. So these are our complicated cases. So that seem a bit complicated. Complicated cases. And here we will use the power of homeomorphism. So let's now consider a solid sphere. So this is a solid sphere. And we know that this is homeomorphic to a cube. That means a solid cube, not a hollow one. Okay, so this is a solid cube. We want to ask what is the Euler characteristic of this solid sphere. Now since this is a sphere, you can easily see that it's very hard to understand how many vertices or edges does it have, right? However, if I use the idea of homeomorphism, I can deform the solid sphere into a solid cube. When I do that, it's very easy to identify the vertices and the edges and the faces. So how many vertices does a cube have? So let's count them. It's 1, 2, 3, 4, 5, 6, 7 and 8. So vertices are 8. There are 8 vertices. How many faces are there? There is 1, 2, 3, 4, 5 and there is this one, so 6. So there are 6 faces, right? How many edges are there? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? There is 4 over here, 4 over here, so 4 and 4, there is 8. And yeah, there are 12, right? Let me try to compute it again. So this is 4, this is 4, so 4 plus 4. And then we have 1, 2, 1, 2. So 4 again, so there are 12. So there are 12 edges. So since this solid cube is homeomorphic to this sphere, we can use the Euler characteristics definition to compute the Euler characteristic or Euler number for the solid sphere, and this is just 8 minus 12 plus 6. So this is 2. Okay. Now let's try to compute the Euler characteristic of a torus or a donut, whatever you want to call it. So we want to find out the Euler characteristic of a torus, right? Again, this is not a very easy thing to identify the edges, vertices of a torus from this figure, but what we can do in this case is that we can use a two-dimensional projection of that torus that we talked about earlier when we introduced equivalence relations, right? So if you recall that a torus is identified with a square or a rectangle as follows, where these two arms are identified like this, and then you have another identification like this, right? And now let's give them some names. Let's call this arm on the left side as A, and since this arm on the left and this arm on the right are the same thing, because we are saying that these are equivalent, so this is also A, and similarly if I call this B, this would also be B. Now to compute the vertices, we assign a name to this point. Let's say this is known as X, and from this identification here you can think that this X is being pushed off from this point to this way, and eventually it will go over here, right? And similarly from here it will go over here, okay? And from here it will go over here. So all these points can be thought of as the same thing. And this is also very clear when you actually draw the circles on the torus like this, the horizontal one, and they intersect each other at only one point. So that's the vertex. So there is only one vertex for a 2 torus, because we write this torus as t square sometimes. So the number of vertex is 1. How many edges are there? You can see that there is only one arm called A, another arm called B. So there are 2 edges, right? And since this guy is filled up, how many faces are there? There is only one face, right? So the Euler characteristic of this torus is 1 minus 2 plus 1. This is 0. In fact, what you can even do is that you can take the torus, use some homeomorphism, and you can identify this torus. That means you can take this torus, you can continuously deform it, and now you make something like a cube, but now it just has a hole inside it. So if I try to draw that, it would look something like this. Okay, and you can now even count the number of vertices and faces from here as well, and you will eventually get 0. Even though the number of vertices, edges, and faces might change, the overall Euler characteristic won't change. Now if I talk about, okay, let's try to compute the Euler characteristic of the Mobius strip. The Mobius strip, it's an orientable surface, and we'll have to talk about non-orientability when we discuss manifolds. So Mobius strip, just like the torus, since if you look at the Mobius strip, okay, drawing it will be a bit hard. So if you look at the Mobius strip, it's not very easy to identify the edges, right? The edges, faces, and all that. So again, we can use the same trick that we did before, is that we can use the 2-dimensional projection or the 2-dimensional identification of them to compute it. So this is our Mobius strip. We want to compute the Euler characteristic of this, and we know that we can identify the Mobius strip as follows. If this is identified this way, this is identified in the opposite way, right? And it's also filled in. Now again, these 2 arms, they're identified in the opposite way, right? But they are indeed identified with each other. Like if I take a point A, it's identified with a point over here, right? So these 2 arms are basically the same thing, because at the end they will get glued to each other. So these 2 things become one. So that's why I'm calling it the same thing. And these 2 arms, they're not identified in any way, so let's call it a P, call it C. And similarly, let's assign a point X, and this is also X. And note that these X's don't get pushed up to the horizontal sides. So if I call it Y, it will be Y. So how many vertices are there? There are 2 vertices, this X and Y's. How many edges are there? There is 1, 2, and 3, A, B, and C. So there are 3 edges, and there is only 1 face. So the Euler characteristic of this Mobius strip is 2 minus 3 plus 1 is equals to 0. And this was an exercise from Nakahara as well. This is an exercise from Nakahara. So this is how you can compute Euler characteristics if the figures are convenient. But most of the time what happens is that the figures are not very convenient. In fact, when you try to compute these Euler characteristics for a complicated surface, instead of using this formula, you can use something called a Gauss-Bonnet theorem to compute it, and we will see those things once we discuss about manifolds and stuff later on. So this is a very nice and fun thing to do. This is a very useful topological invariant, and the one thing I would like to comment is that it can be shown in general that if your surface, if your space, that means your topological space, has a genus of G, then the Euler characteristic is given by two minus 2G. This is a general formula, and this symbol over here, it means surface with genus G. And now you can easily verify them as well. Just check these cases. In the torus there is only one genus, right? So for the torus, G is equals to 1. So the Euler characteristic for this two torus where there is only one genus, you have 2 minus 2, which is 0, and that agrees. For a solid sphere, there is no genus, right? Because it's solid, there is no holes inside it. So for that, you will have 2 minus 0, which is again 2. And you can check that all the other cases agrees as well. So this concludes our discussion of the computation of Euler characteristics for these polyhedras or the figures in 3D. The next thing we're going to talk about is something called a connected sum, and this connected sum is actually a connected sum of the topological spaces. So now let's move on and talk about connected sum.